Okay, so welcome to everyone for the CMI seminar. And today we are very happy to have Paramjit Singh, who is our recent alumni who just left CMI last year. He from Humboldt University in Berlin. Currently, is there, and he will now today talk about transversality and symmetry of pseudoholomorphic holo covers. Thank you. Yeah, Paramjit, go ahead.
Yeah. So thanks everyone for joining in, and thanks to CMI for the opportunity to give a talk here. I mean, these are difficult times, and I hope all of you are doing well. So today I'll talk about transversality issues for holomorphic curves and how symmetry factors in when we are trying to talk about multiple covers of those holomorphic curves. The talk is broadly divided into three parts. In the beginning, I'll give some relevant definitions and so on and so forth, whatever we need later on for holomorphic curves, and give the setup for the nonlinear Cauchy-Riemann equation and how the moduli space is for simple curves. So this will be a very brief overview, and then we will move on to the case for multiple covers. What happens for unbranched covers, what we can say for branched covers, and so on and so forth. And in the end, I will outline the main results of the paper and the main theorem of the paper, which helps prove those results, which is based on stratification. Okay, so let us begin. So we are going to talk about holomorphic curves, and for that, we need some definitions. So let MJ be an almost complex manifold. By this, I just mean that J is an automorphism of the tangent bundle of M with squares to negative of identity. And let sigma be a closed Riemann surface. So we will be talking about closed curves here. And so we look at smooth maps, U from sigma to M, whose differential commutes with the corresponding almost complex structures on both sides. So such that J composed TU is TU composed with J. Such a map is called a J holomorphic map. For the obvious reasons, it's J holomorphic with respect to the almost complex structure on the target manifold. Okay, so we study J holomorphic maps because they are very useful in symplectic topology, starting with Gromov's introduction in his 1985 paper, in which he proves some results about how symplectic topology is in some sense rigid. The most famous result being of non-squeezing theorem, that if you have such a map, then the area can never be squeezed. Area being defined as an integral over the domain Riemann surface and so on. Okay, so we want to study holomorphic maps. So I'll abbreviate J holomorphic maps by just holomorphic maps because that is what we will be studying. These maps satisfy many properties which are analogous to honest holomorphic curves in complex analysis. And to study these curves, we take a sort of a global perspective, which means that to get some information about these curves, we rather look at the space of all curves and try to deduce what properties we can get for these maps from that perspective. So, I mean, if we denote by B the space of all smooth maps between sigma and M, and if we denote by E infinite dimensional vector bundle, I'll just write it in quotes because it's infinite dimensional, such that for any map in this space, I define this vector space of U star TM valued 0, 1 forms, then we can show that these things form a bundle over B. And then we can define these particular section by using this definition as and this turns out to be a section of this bundle. And we have that the J-holomorphic maps, which I'll denote it like this, are precisely the zero set of this section. That is the points in the base, which are mapped to the zero section of the bundle. Okay. So now we want to, in some sense, come to the fact, we want to describe how the space of all such holomorphic curves looks like. And one of the natural things to guess is that, is it a manifold? And it turns out that under suitable hypotheses, indeed, it is a smooth manifold. But the way to prove that involves this operator. Just like in usual finite dimensional differential geometry, we have that if we have a smooth map between manifolds, then inverse image of any regular value is a smooth submanifold of the domain. Similarly, we will try to use that. We will try to prove that this for this section, it is in some sense, zero is in some sense a regular value of this section, and hence the inverse image of the zero section is in fact a smooth manifold. So for that, for the hypotheses, I would have to introduce the notion of what simple curves are. So recall from complex analysis that if you have two closed Riemann surfaces, then any holomorphic map between them is either a biholomorphism or a cover of some kind. So similarly, if you have a J-holomorphic map from sigma to say M, then you can always factor out a simple curve out of it, or a curve which would the analog of a biholomorphic map from normal complex analysis. So, okay. Simple curves in the closed settings are also the same thing as somewhere injective curves. And what that means essentially is that the curve is injective, and the derivative, the curve is injective somewhere. So there exists at least a point Z such that it's a regular point, as well as the inverse image. I mean, no to, okay, so I can write it like this. So there exists at least one such point, and you can later on show that the space of all such points is open and dense. Okay, anyway, so the point which I'm...
I have a question.
Yes.
So I guess with a simple curve, the map is everywhere finite, right?
What do you mean finite?
Meaning, if you have a simple curve, then the map from the simple curve into MJ does not have positive dimensional fibers.
No, of course not.
Yeah. Okay. Okay. I mean, just as in the case of complex.
Yes, exactly.
Okay. Okay. Yeah.
So, so what I wanted to say.
Okay.
Yes. Is there a question?
No, that's it. Okay. Yeah.
Okay. So I'm saying that any holomorphic map can be factored via a simple map. So we, in fact, we can find another Riemann surface such that we can factor out a simple curve out of it. And I mean, the result we get after factoring it out is a holomorphic cover. Okay, and so by the way, this equation is the holomorphic curve equation, or what we should call the nonlinear Cauchy-Riemann equation. So holomorphic maps are the solutions to the nonlinear Cauchy-Riemann equation, just like in ordinary complex analysis. So now let me say something about the moduli space of simple curves. It turns out that if we consider the space, okay, so let M omega this time be a symplectic manifold. Be a symplectic manifold, and we are going to make some statement. We are going to look at holomorphic curves inside this manifold. So we would have to choose a certain holomorphic, almost complex structure, which is in some sense compatible with omega, which I'm not going to define here, but you can look at the relevant literature. So, and suppose this is a closed Riemann surface, and suppose this is compact as well. And we have a theorem that if we perturb this almost complex structure generically, which really means is that we consider the space of all almost complex structures, and there we have a co-meager subset for which whatever I'm going to write now holds. So throughout this talk, I will keep repeating this for generic something, often for generic almost complex structure. So then the space of all curves. So I'll just write here vaguely, J holomorphic curves. This is a smooth manifold. And it has a dimension given by an index formula, which I'm not going to write right now. So so by the way, we also specialize the curves to have this special property that if you have a fixed homology class of the target manifold, we also would like to look at maps which represent this homology class, which is to say that they push the fundamental class of the closed Riemann surface into this homology class. So this is just for making things more more easy to handle, and so on and so forth. Okay, so this is the story about simple curves. Now the natural question which arises is, what happens for multiple curves? Can we make a similar statement about multiple covers of holomorphic curves? So what about multiple covers? Do multiple covers of holomorphic curves form smooth manifolds just like this, or do they form orbifolds, and so on and so forth? Okay, so suppose U from sigma to M is a closed curve, so closed J holomorphic, and suppose phi, okay, maybe I should have, okay, just a second. one of the advantages of dealing with technology is you can edit very easily. So suppose we also have a unbranched cover of closed surfaces, closed Riemann surfaces. So suppose phi is a D2-1 holomorphic cover. Then composing the two maps, we get a new map here, which is U composed with phi. So we can, in some sense, start saying, okay, what are all the D-fold covers? Holomorphic, what are all the J holomorphic curves which are D-fold covers? Then, I mean, if we were to look at the space of all D-fold covers, and if it was a manifold, or and so on and so forth, then it would be reasonable to expect that its dimension would be given by the index of this curve. The index being defined as the index of the linearized Cauchy-Riemann operator, or the Fredholm index. So suppose, so I'm writing this term virtual here, that just means that often the spaces of the curves we consider, they are not manifolds, but for generic J, we do expect them to be manifolds. And the manifolds will have a particular dimension. And because that's the expected dimension, we also call it the virtual dimension. So suppose the virtual dimensions of the moduli spaces containing U and U circle phi. So this thing, as I said, is the same as the index of the curve of. Then we have this relation. Now, if U was a simple curve to begin with, then we know that such a curve would lie in a moduli space, which is a smooth manifold of certain dimension, the dimension being index of U. That is non-negative. I mean, we can either have a positive dimensional family of such curves or a discrete set of such curves. But then this relation tells us that this index should also be non-negative in such a case. So, I mean, so there is no apparent reason why there is no reason why U composed with phi could not achieve transversality. I mean, we don't have any obstruction to that. But the usual ways of holomorphic curves that we use for simple curves does not generalize to this situation, because there we in fact use the existence of a somewhere injective point to prove surjectivity of an operator. So that proof does not generalize to this unbranched setting. So by the way, this is a unbranched cover, and for branched covers, the things are more subtle. Okay. So yes.
So like when you say the virtual dimension, is it independent of the J being chosen?
So we will be choosing J in a certain family, but okay. The statement is for generic J. In that family, regardless of which J you choose, the dimension is independent of that.
Okay. Thank you. Yeah.
I guess the virtual dimension is like Euler characteristic. So
Euler characteristic plus the Chern number of the
deformations. That is why it is doesn't change.
Yes.
Yeah.
Okay. So we continue our discussion for multiple covers. And one of the ways in which we can study multiple covers is by studying the automorphism group of the cover itself. So we have some sort of symmetry in the picture. And the entire crux of this discussion is to talk about how symmetry interacts with transversality. So let us give an example in finite dimension.
So, Paramjit, is the issue
Yes.
that you may have a map from the cover to the almost complex manifold?
Yes.
And this map, the composed map, the original map, it could deform into a map which does not factor through the action of the group. So
Yes.
transversality will hold in the larger family, but not within the smaller family of things. Is that the issue?
No, yeah. So one of the issues which can happen is curves which are close to a D-fold cover need not be covers.
Need not be covered.
So
Yes,
as you said, so in that case, we cannot really get transversality, right? Because it does not look like a manifold of covers nearby.
Right. So in fact, generically, you would expect that to be the case, right? That why should every deformation factor through the default cover?
Indeed. Yeah, and that is the problem of transversality for multiple covers. But for certain special conditions, for certain special situations, which I will talk about in a bit, like if you have a Calabi-Yau threefold, and if you're looking at holomorphic curves inside that, then we have a notion of super rigidity.
Okay.
Yeah, so I will talk about it. Okay, so let me go ahead with the example in finite dimensions. So suppose you have a smooth map from R2 to R2, say smooth, and suppose it is Z2 equivariant. In this sense, so now one can show either directly or by using methods which are similar to showing that generic functions on a smooth manifold are Morse, that every such map admits closed perturbations for which, so very important, closed Z2 equivariant perturbations for which 0, the origin, is a regular value. Is a regular value. So, I mean, so in this case, we can do it, but not necessarily for the reason we think. I mean, we do not necessarily have transversality. That's what I am trying to say, because note that the entire x-axis is mapped to the origin for a Z2 equivariant map. So we may not have transversality of the space of such curves with the zero locus. But what we can have is something called clean intersection. So the zero cleanly. And even for clean intersections, we have that the inverse image is a smooth submanifold. So I'll briefly define what clean intersections are. Okay, so this notion of clean intersection is in some sense the only other thing you could do for the intersection set to be a manifold other than transversality. So we say that if M and N are two submanifolds of, say, a manifold X, then they intersect transversely. If at all points of the intersection we have that the tangent spaces span the whole tangent space. So the other thing you could do was look at the intersection of these two tangent spaces. So if it turns out that the intersection of the two tangent spaces is in fact the tangent space of the intersection, then we call such a thing as clean intersection. And under suitable hypotheses, then it turns out that M intersection N is still a smooth manifold. It's a smooth submanifold. Okay, so now because we took this global perspective of holomorphic curves being the zero set of this del bar section, a lot of the theory of holomorphic curves really is about understanding bundles and zero sets of sections of those bundles, and when those sections are transversal to the zero section, when they intersect the zero section cleanly, and so on and so forth. So it's okay. Okay, so when we want to talk about Euclidean transversality, we are going to set up some finite dimensional bundles and so on and so forth. So suppose we have a n-dimensional orbifold, and we have, say, an orbi bundle E over M of rank M. So what this means is that there are certain points. So M is mostly a manifold, but there are certain points of M which have local isotropic groups, or groups such that a neighborhood of that point looks like a quotient of an open set of Rn by some finite group. So every X in M has a finite group, Gx, say, and a neighborhood Ux of M such that, so I'm also defining the word orbi bundle here, such that E restricted to Ux is just this for some linear action of Gx on Rn. So we already have some sort of a presentation of Gx and a neighborhood O in Rn of the origin, let's say. Okay. So we have an orbifold and an orbi bundle, and we want to ask the question that if we look at sections of that orbi bundle, do they intersect the zero section transversally, or at least cleanly? So the question we want to ask is generic. So for all sections, we are going to look at some sort of generic sections. And we have certain theorems answering this question in some contexts. So I'll just mention a few. So if it turns out that the dimension is the same as the rank of the bundle, and moreover, the isotropic groups are small enough, then we have clean intersection. Then generic sections of E intersect the zero section cleanly. And we also have another theorem which says that generic smooth functions, just like in the case of a manifold, for an orbifold as well, they are Morse. So how does one go about thinking about how to show these kinds of results, or what is a good perspective to take? And the perspective which we will take here is that we will, so first of all, Gx can vary from point to point. For different x, we can have different finite groups. So we will, in some sense, break up our manifold into parts where the local isotropic groups act in the same way. So that is the notion of stratification. So stratification by symmetry. So suppose we have a finite group, and suppose we have representations of that group. Remember that for an orbifold, Gx has a linear action on Rm, so we already have a notion of representation. So suppose we have representations like this and like this. Then define this submanifold, which is going to be a part in our decomposition. So take all points where the isotropic group is G, and it acts on DXM as rho and on EX as tau. So we have a submanifold, and we also look at the subbundle, essentially, which is going to be the subbundle over it, as the restricted bundle to this submanifold, such that G acts trivially on B. Right? So now we isolated ourselves to the action of a particular group in a particular way. So a particular group in a particular way. And now we already have fixed representations. So, but these representations need not be irreducible. So we will look at its irreducible components. So let theta I from G to so let this denote the real irreducible representations of G. So let's say theta 1 is the trivial representation. the first one, and suppose mi of rho is the multiplicity of theta I in rho, then we have that dimension of m rho tau. These things can be checked with a bit of unfolding the definitions. So we finally have that our orbifold is a union of these disjoint submanifolds. M rho tau, and each of these submanifolds have the corresponding subbundles over them. Okay, and so let us make an observation that for all sections of my orbibundle, sigma of a particular submanifold always lies inside this subbundle over it. So yeah, and this means that sigma is not transversal to the zero section at a point unless tau is trivial. Okay. We have a transversality result for this kind. So let's say standard transversality. Here, because we are looking at equivalent sections, and the group is fixed, as well as the action of the group on the base as well as the fibers is also fixed. So for generic sigma, we have that its restriction to the subbundle, to the submanifold, is transverse to the zero section. Is transverse to the zero section of this bundle, not the whole bundle. Important. So this is for all G, rho, and tau, and so on and so forth. So, I mean, we have partial transversality here. So from this, we cannot conclude that M sigma is we cannot even conclude if it's a smooth orbifold from this. It has paths which are smooth submanifolds, but it itself need not be a smooth orbifold. But sometimes we can push this to say that it's a nice enough orbifold, and so on and so forth. So for that, we talk about what really defines transversality and how that interacts with symmetry and so on. So I will quickly write down what I mean by that. So what is meant by transversality? So we have that at every point of the base, we have a particle linearization. So what one should, so by the way, this is an abstract theory. I mean, I'm explaining all this in finite dimensions, but the sections which one should have in mind are the del bar section of this bundle. Note that the holomorphic curves are the zero set of this section. And when we are talking about holomorphic covers, then it turns out that the space of covers will be an orbifold, and we will be looking at equivariant holomorphic curves. I'm saying equivariant under the action of the deck group of that cover. Okay, so we have a linearized operator. And recall, that theta I were the irreducible representations, and let di be the dimension of the irreducible representation. Then we have that the linearized operator is in fact Gx equivariant, and by application of Schur's lemma, we have that by Schur's lemma, dx splits with respect to the isotypic decompositions. Of rho and ex of tau, like this. So what you should have in mind is we have a linearized, the vertical part of the differential, which is the linearized operator is equivariant under the action of the isotropic group. So that is going to give us irreducible representations. Because every representation is a direct sum of them. And with respect to those irreducible representation, with respect to that decomposition, our operator is also going to split. So when we want to talk about the surjectivity of this operator, which is what we need to prove that its zero set is a smooth manifold or something like that, then it is useful to understand these operators individually. So in fact, these operators have Fredholm indices. And because the first representation was the trivial one, we know that D1x is surjective if sigma is generic. So then we can divide our manifold into parts according to these numbers and show transversality for them individually. So this is what we use to, tackle the problem in the case of unbranched covers, as well as in the case of branched covers, where the branching data is fixed. By that I mean, we know the branching orders at the critical points and so on and so forth. Okay. This was a finite dimensional setup for what we will do now for the del bar section. Yeah, so this is what we do in the paper. That is how we get the stratification result. Let me move ahead and talk about what are the main results of the paper. These are the results which we set on to prove, and then I will briefly talk about how these results can be framed in terms of certain dimension counting arguments and lay out the stratification theorem which we need to prove, which gives us all these results. So the main three results are the following. The first one is theorem B of the paper, which is, it's the theorem B because I chose to consider it first. It's the unbranched transversality. And roughly what it says is the following. So for generic, almost complex structure, for all simple curves, U from say sigma to M, and for every unbranched cover, phi from say sigma tilde to sigma. So all of these are closed Riemann surfaces. The curve U composed with phi is Fredholm regular, which technically means that the derivative, the linearized Cauchy-Riemann operator for this covered curve is surjective, but it also means that this lies in a smooth manifold. What I mean to say is that if you were to look at the space of all holomorphic curves were covers of this fixed holomorphic curve U, then that would also be a smooth manifold. So this was for the unbranched case. In general, for branched case, we have certain subtleties, as we mentioned earlier, harder to achieve transversality. So let's see what we can do. So suppose we are looking at a cover like this. U is a closed simple curve, and phi is a degree D branched cover. And suppose ZD phi is the algebraic count of branch points. So we have the Riemann-Horwitz formula. Relating the Euler characteristics of the two curves. And we also have the index formula for the individual curves. For closed curves. So combining the two, because the index formula has this Euler characteristic in it, combining the two, we get index of U composed with phi is D times the index of U. So here N is, twice of N is the dimension of M. So if you look at this formula, if we have that index of U is 0, that is, U lies in a discrete set of curves, then we see that the index of U composed with phi is negative. It's negative if N is greater than 3. So if index of U is 0 and N is greater than 3, then index of U composed with phi is negative. So in this case, there is no reason to expect transversality. If moreover, what we tried to do, if what we tried to do was, if U was regular, And if we varied both U and phi in their respective moduli spaces, so I'm not properly defining what perturbing phi in its moduli space means. But if we made those appropriate perturbations, then we would have this formula. I mean, what I'm trying to say is that if U is regular, then U lies inside some moduli space. And phi also lies inside some moduli space. And its dimension is given by twice the algebraic count of branch points. So we have U and we have phi. Then, I mean, in principle, we should have U composed with phi living in a space of dimension which is as big as the sum of these two dimensions. So this is something reasonable to expect. This is what we should have if U composed where phi were Fredholm regular. And one of the ways in which we can have that is if, say, phi has R critical values, then if we have index of U is greater than or equal to n minus 1 times R, then we would have this condition. And the theorem C of the paper says that this condition is in some sense sufficient. So, I mean, it was necessary for us to have this condition. This condition implies this condition. And what we are trying to say is that, yeah, it's in fact a sufficient condition that if we have this, then we are going to have transversality for branch covers. So, in interest of time, I'll write it a bit vaguely, which is that for branched covers, so for generic J, for branched covers, can find arbitrarily close regular covers. Okay. So now let me go towards the definition of superrigidity. Okay, so let us again come back to what problem we had. So the problem we had for the index here is that if index of U is 0 and n is greater than 3, then we don't expect this to lie in a positive dimensional manifold because its index is negative. So, and what is the index really? The index is really the index of the linearized Cauchy-Riemann operator at that point. Now, there's also a theorem that if our curves are immersed, then instead of looking at the full linearized Cauchy-Riemann operator, we can look at its restriction to the normal bundle of this curve. So can consider which is the restriction of our whole operator to the normal bundle. Then instead of the index formula which we had here, in terms of the normal bundle, we have this index formula. And this is very useful because if you had index 0, so by the way, one thing which I did not elaborate was that Fredholm regularity of U can be characterized in terms of surjectivity of the whole operator or of its restriction to the normal operator, which is not very, I mean, one direction is not very difficult to see. So for immersed curves, looking at the whole linearized operator is the same as looking at the restriction to the normal bundle. So, but if we consider the normal bundle, if we consider the normal operator instead of the full operator, then the index formula changes, and the index formula becomes this, and this shows us that it can be injective. Now, what does injectivity of this operator mean? Remember that sections of the normal bundle can really be looked at as perturbations which you can make to a curve. I mean, if you had a curve U and if you had some section of the normal bundle, then to get nearby curves which are nearby to U, the thing which you can do is make perturbations by those sections. So if you look at it from that perspective, the injectivity of this normal operator, the normal Cauchy-Riemann operator for the cover, it really means that all the nearby curves to this curve are also covers. So again, let me just repeat that. So this injective really means that U composed with phi can never be the limit of a sequence of somewhere injective curves, which is the same thing as saying that the only other curves near U composed with phi are other branch covers. So this is the notion of superrigidity. So I'll just state the theorem and I briefly say what its history is, or rather an alternative formulation. So if we have the dimension at least as big as 6, then for generic J, every simple index 0 J holomorphic curve is super rigid. The definition of super rigidity is just that we need to have closeness and connectedness. A simple curve whose index is 0, which is an immersion. By the way, this we can obtain by choosing appropriate J. And all covers, for all covers. So the normal Cauchy-Riemann operator for all covers is injective. Right? So I've almost run out of time here, and let me make some decisions of what I want to say after this. Okay, So this is the notion of superrigidity, and this condition, I mean, it was part of a conjecture by Brian and Pandhari Pandey of 2001, an alternative characterization for this is that the zero section, in fact, intersects the zero section cleanly. Clean intersection between the Cauchy-Riemann section and the zero section is precisely this condition. One can see this by unfolding the definitions. So to prove all these theorems, so let me just say theorem D implies all of the above, and it is the most important theorem of the paper, which is proved by breaking up our manifold into various parts and so on. So instead of writing the theorem for our full problem, let me write it for what it would be in finite dimensions. So we have some sort of stratification of our manifold. Let me say how that works. So remember that earlier we had some sort of decomposition of the linearized operator for a section, for an equivariant section of an orbital bundle. Then note that Gx will act on the kernel of these operators as well as co-kernel of these operators as the irreducible representation theta I with some multiplicities. And then we can, in fact, consider the space of all the points where the kernels and co-kernels of these, the kernels and co-kernels of these components of our original Cauchy-Riemann operator have certain dimensions. So suppose K is some vector, and say Kn, and C is another vector. If we look at, I'll just take 2 minutes more. Such that the dimension of the kernel of Dix is this, and the dimension of the co-kernel of the same thing is this. That is, once we fix the dimension of the kernels and co-kernels, then we have a theorem that for all generic sigma, for all choices G rho tau K C, this is a smooth submanifold, and it has co-dimension summation Ti Ki Ci, Ti being dependent on what kind of irreducible representation theta is. I mean, we can have real type of representations, just like in usual representation theory, we can have real type of representations, complex type, or quaternionic type. Depending on that, Ti is either 1, 2, or 4. So how you should think of it is really a bootstrapping of ideas. The first idea, one of the components being usual representation theory, and the other component being the simple fact that if you have if you have, say, two vector spaces, and if you're looking at the space of all maps, linear maps between those vector spaces, and if you wanted to in fact look at the space of all maps with a certain dimensional kernel and a certain dimensional co-kernel, then the space of all such maps would also be a smooth manifold. And that idea is again used here to prove this result. Thanks for listening. I will stop here, and if you have questions, yeah.
Yeah, thank you, Paramjit, for the nice talk.
Very nice.
So if anyone has questions, please ask.
So I guess the complex analytic or algebraic geometric phenomenon is in a, say, Calabi-Yau threefold. There are nodal curves such that every deformation is a nodal curve. That
but nodal curves and covers, they are different, no?
So see, I thought your point, I think one of the, yeah, you have groups acting.
Yes.
Well, yeah. So what is the, so in the case when you are working in the algebra-geometric context, what is the super rigidity phenomenon? I mean, so you have so you have some kind of curve in a say a threefold. I guess you
right.
Calabi-Yau threefold, such that every deformation of that is also that same kind. So and such that if I want, and so clearly this is a singular curve.
Yeah.
And such that if I want to express as a map from a smooth curve, then I have to go to a sort of cover. That is a phenomenon, right? I mean,
so I mean, there are two things there. So one of them is when we want to compute chromobit invariance, and the other thing is that we do not have transversality there.
No. So I'm trying to understand the second phenomenon, which is
right.
purely algebra-geometric way. This
right.
rigidity business. So when you have one of those, when you have a map from a Riemann surface to, say, a Calabi-Yau threefold, that factors through, which is multiple, so it factors through a quotient by a group. And then phenomenon is that every deformation of the factor, see what is?
Yeah, so so that curve factors through a simple curve.
There's a simple algebra geometric phenomenon that I'm kind of trying to understand.
Yeah. So there's a so that curve factors through a simple curve, right? A simple algebraic curve, whatever the definition is.
So you have a map. So the point is that there is a map from a curve to your say threefold, which passes through a quotient of the original curve by a finite group.
Okay.
So that is the business about. So then the second curve is what you call a simple curve.
Yes.
Now, but the rigidity phenomenon is that deformations of this are also
covers of that same curve. Are covers of that simple curve. Of
the original, so of the fixed simple curve, is that the?
Yes, of the fixed simple curve. That is the notion of rigidity.
But so you mean there are, okay.
So curves nearby to this cover are also covers of the same underlying curve.
Okay, I have to think about that. Okay, yeah, but this is a very nice talk.
Okay, thank you.
Yeah, so okay, let's thank Paramjit again, unless there are any more questions. Okay, thank you, Paramjit.
Okay. And good luck to all of you.
Yeah.